Today I'm joined by Dr. Elias F. Combarro, a mathematician turned computer scientist and professor at the University of Oviedo, a member of the CERN Quantum Technology Initiative Advisory Board, and a driving force in Spain's quantum community through QSpain. He has published extensively across computability, machine learning, and quantum algorithms. He has also authored two books, namely A Practical Guide to Quantum Computing and A Practical Guide to Quantum Machine Learning and Quantum Optimization. I hope you enjoyed this episode.
So thank you for making your time today, Elias, for being here. We'll just dive straight into the questions now. I just wanted to know, my first question is, what really sparked your interest in quantum computing and how did your journey begin?
Mhm. Well, first of all, thanks for having me. It's a great pleasure, and I'm really excited about this interview. I've always been interested in quantum computing. I did my PhD in a somewhat related field, which is computability theory, which has to be also with models of computing and things like that. But at that time, I didn't see quantum computing as something that you could use in practice. So that was something that was always on the back of my mind, but I didn't really pay a lot of attention to the field. But like, I don't know, 15 years ago or something like that, we were working on this problem that required a lot of computational power. I'm talking about million hours computing uh, time or things like that. So kind of joking, we here at my group, we mentioned, well, when we have quantum computers, we can go back to this problem and maybe try again, right? This was a very niche problem in the classification of certain algebraic structures that we did with the computer. And then a few years after that, we learned that IBM was making quantum computers available online. And it was like, okay, this is what we were waiting for.
Yeah.
So then we started learning about quantum computing and how, especially how to apply quantum algorithms to that kind of problem. And I must say, I fell in love with quantum computing. It was exactly the kind of topic that requires knowledge from mathematics, computer science, physics. So it's wonderful. So to me, it was like, okay, this is what I've been waiting for all my life. This is exactly what I wanted to do.
That's super interesting. Actually, the fact that it's so interdisciplinary and people from
Yeah.
different fields are able to make use of quantum computing is super interesting. So my next question would be, you're having so many roles, so many hats that you wear as a professor, as a researcher, now an author. So how has all these different roles shaped your perspective of quantum computing?
Mhm. Well, I think that you need both to be a researcher and an educator in order to be able to really like have a feeling of what the field is about in order to better write material about quantum computing. So to me, being a researcher and being an educator has been very, very important to being able to know what are the main topics that students need to know about, and also what are the main difficulties that students find. I think this is also very important because if you are only a researcher, sometimes you don't know what is difficult for people who are starting to learn about quantum computing. And
Yeah.
I teach at different levels. So I have students with a background in mathematics or physics or computer science, and they require different things. So it's of course it's important to know what is being done now, what is the state of the art in quantum computing, but you also need to interact with students to know what they need or what they require in order to master the main algorithms.
That's so true. I found that with some of my teachers and professors as well, that they sometimes forget how difficult it is for a beginner to get started, or where they might get stuck, and they assume that you understand what they're teaching. So that's really important for professors and educators to keep in mind. That's a great point. My next question would be, was there any particular moment that made you feel like I need to write this book?
Mhm. Well, I think, well, I must say, I've always wanted to be an author. Okay. In fact, when I was young, like many years ago, when I was 10 or something like that, I wanted to be an author of science fiction books. I love science fiction. I also wanted to be a heavy metal guitar player, but that was kind of more difficult
Okay.
because I'm not talented. So I've always wanted to write books, but at the same time, I didn't find any particular topic in which I thought I could contribute. But then when I started working in quantum computing and I started teaching here at the university and at several other different places, I noticed that there was a lack of a textbook that included both the algorithms, the theory, the mathematics, and the computer programming part, like books with code. To me, it was really shocking when I started learning about quantum computing that there were many books, many very good books, and many popular books, but none of them had quantum code. So you had then to learn how to use Qiskit or CERN or Penny Lane or whatever on your own. And then you needed to learn how to translate all those algorithms from the mathematical
To the code.
description, the mathematical formulas into code. So
Yeah.
what we wanted to do was to, write a book in which you had both the theory and the code. Okay, so this is exactly this is what we did with our first book. This is our second book. Our first book was on quantum optimization and quantum machine learning. And for that kind of topic, I think it was even worse because there was not really a book that had all this theory and code together. And this is exactly what we also try to do with the new book, especially because, well, now here at my university, the University of Oviedo, we have new courses on quantum computing, and the students need a textbook. Most of them are data scientists or computer scientists or mathematicians or physicists. They want to have something that they can rely on that has that includes both the theory and the practice.
And that's so true, actually. Having the code and the theory together makes it so much easier for a student learning quantum computing for the first time. And that's another reason I love the book so much. Apart from the little bits of humor and jokes thrown across the book, I really love those aspects as well. Um, my next question would be, can you share one chapter or section of the book that you're really proud of?
Well, I think this is an easy one because maybe you notice that the longest chapter in the book is the one about Shor's algorithm.
Yes.
And this is something that it's always a challenge to teach to students. In fact, I have a friend that many years ago told me, I challenge you to teach me all the details of Shor's algorithm. So this is my response to that challenge. We try to make it very accessible and with all the details, and this is difficult. I had to rewrite the chapter several times in order to make it more easy to follow and to include different things, but not too many details. For instance, we have a section on the quantum Fourier transform, which is, of course, essential to Shor's algorithm. And to me, it was difficult to know exactly what to include and what not to include. I think this is also important. So for instance, we don't give a full proof of why the circuit that you use for the quantum Fourier transform actually works. But I'm very confident that with the details that we have included, anyone with enough interest will be able to provide a proof that it works. Okay, so we have like enough of the argument for anyone who is interested in really getting all the details to provide all these details just by computing a couple of formulas. So to decide what to include, what not to include, what are details that you can skip and still understand everything, especially with such a complex algorithm. I think it was challenging, but I'm quite satisfied with how it came out.
That's great. Actually, this ties in with my next question. How did you balance maintaining the mathematical rigor that is required to teach quantum computing and keep it beginner friendly as well?
Yeah, this is also difficult because we have in mind many different readers with different backgrounds. So people who are developers, people who are physicists, people who are mathematicians, people who have an interest in quantum computing. So it's difficult to know what the reader will know in advance. So we try to not assume that they know anything especially difficult apart from knowing what a vector is or what a matrix is. So we use different tools to provide different levels of detail. So there is the main text with the core ideas that you need to know for sure, you cannot skip. Then you may have noticed that we have these boxes, we love boxes. These to learn more boxes, which we include additional ideas that you can skip on a first read, and you will not miss the main argument. You will understand everything. But then if you want to deepen your understanding, you can read these learn more boxes, and then you will have we hope a deeper understanding of the subject. And we also provide a lot of appendices with ideas that we don't include in the main text because they will lead you astray from the main path, but can get you to speed if you don't know, for instance, about vector spaces or things like that. And then we also provide a lot of references to advanced books or to papers or to websites in which you can learn more about this kind of topic. But we try to make this very, very inclusive for anyone that has just a basic knowledge of linear algebra. And then advanced ideas can be further explored with these boxes or with these references.
That was actually another point that I really loved, that you had given these boxes and the appendices and the references, which it in itself is like a gold mine of resources for anyone to further continue the learning in quantum computing. And now I wanted to ask, what are some common misconceptions that you see people having about quantum computing? People who are even tech savvy in the other industries as well. What do you see them having as misconceptions?
Yeah. Well, I'm even now surprised after many years of giving talks and talking to people that there are many, many misconceptions. In fact, a couple of years ago, I was asked to write an article for a magazine here in Spain, and then it was later republished by BBC.com on exactly on the myths and realities of quantum computing. What people think quantum computers are and what they are not. And in fact, some of the ideas in that article are included in the first chapter of the book, because I find once and again that people think that quantum computers are magic devices that solve any problem. We all have heard this idea that quantum computers explore all the solutions or all the options at once, and then something magical happens and the problem is solved. And this is something that, to me, it's kind of surprising, because when I was not yet studying quantum computing, like, I used to read this news or these popular science books. Oh yeah, this is what happens. Quantum computers just explore everything at once, and I didn't understand what that really mean. But then when you study the algorithms, you notice that, well, this idea of using superposition, of like exploring all the options at once, is just a tiny part of the algorithms. It's just the beginning. You can do this quite easily, but then you have nothing. You have to work a lot in order to retrieve the actual solution and the value from all those options, and to make more likely to, when you measure the state of the computer, to obtain an actual useful result. And then this is something that we have tried to make clear throughout all the book, that the role of interference. People think that superposition, entanglement are the main ingredients in quantum algorithms, and of course they are very, very important. But to me, interference is the unsung hero of quantum algorithms. Without interference, you get nothing. So this is a very common misconception, that, well, to rely on this superposition and everything falls in place, and it's not true. It's not true. In fact, most of for instance, in Grover's algorithm, most of the operations are trying to improve the odds that you find the element that you want to find. And this is done not with superposition, but with interference.
Yeah, that's a great point, actually. And I've seen that most people, they're either polarized about it by being either completely for it and exaggerating the truth, or completely being against quantum computers and trying to disprove it, even if they've not really gone in and put in the work and learned about quantum computers themselves. It's just because it's popular to be contrarian, they attach themselves to the belief that quantum computers are not going to do anything, which is a thing that gets me upset. But yeah, can't change some people's minds, I guess. My next question would be, what quantum algorithm did you find most elegant and fascinating, apart from the ones that you've covered in your book, while you were a student learning about it, anytime, which was your favorite?
Well, in fact, it's difficult to choose just one, because there are so many ideas. For instance, we decided to include in the book this idea of quantum money. That is really not useful, but to me it's fascinating that you can, like, create, at least theoretically, a banknote that cannot be forged. This is, to me, it's incredible, just relying on the properties of quantum mechanics. But I should say that I love Grover's algorithm. This is my favorite one. Probably not the one that most people would choose, because, Shor's algorithm is so important because of the relevance for cryptography and this kind of thing. But to me, Grover's algorithm is geometrically very beautiful. In the book, we try to give both the geometrical intuition behind the algorithm, but also the algebraic explanation, and how they interplay with each other, and how when you study one and you see the geometrical picture and then you go back to the formulas, how you obtain a deeper understanding of the algorithm. This is very beautiful. And the idea that, well, this algorithm is used to find an element in a database or in a vector, in some collection of information that is not sorted or organized in any way. But you need to operate a certain number of times, and if you operate more than that number of times, then your probability of finding the element will decrease instead of increasing. To me, this is something that when I was learning about this kept me literally awake at night. It was like, this is impossible. Okay, you are looking for something, you look more, you spend more time trying to find it, but then your probability of finding it is smaller. This how does this work? And it made me really try and want to understand what is the actual behavior of the algorithm. And I think this is why I love it so much.
Well, that's so true. That's a case with a lot of algorithms, a lot of concepts in quantum computing and quantum mechanics for sure. My next question would be, what is an area of research that you're looking forward to right now in quantum computing?
Yeah, I'm very, very excited about, I don't know if you've heard about neutral atoms computers.
Uh-huh.
Because, well, I was a visiting professor at Harvard University last year at Susan Yelin's group, and they are working in this kind of computer. Also, Mikhail Lukin's group is working on this kind of computing. They have this, they have founded this company called QEra. They build these nice read-bear atom quantum computers. And here in my region, now we have an expert, Daniel Barredo, who used to work with people at Pascal in Paris, also with this kind of technology. And it has been announced very recently in the last month or so that we will have a neutral atom quantum computer here in my, not in my university, but in a research institute very close to where I live.
That's great.
So, in fact, tomorrow I will be visiting their lab to see how this is coming out. And I'm super excited about this because, well, my region is kind of small. It's not Barcelona or Madrid or one of these big cities in Spain. And to have the opportunity of working with these researchers who are really top researchers in the field, and to be able to try and see what are the applications of this new technology, to me is fascinating.
That's amazing, actually. Usually people, when they think about quantum computers, they think of the superconducting qubit technology, but they aren't aware of the photonics and topological and neural atom quantum computers as well. So that's great that you mentioned that.
If I may add something, I
Yes,
think
yes.
that is also a very interesting topic, because I'm not an expert in hardware, but I see that there are many options, the ones that you've mentioned, of course, superconducting qubits and all that, or ion traps and things like that. But I'm sure that there will be a breakthrough in the next few years that will change the landscape. So I think we have not seen what is the kind of the quantum computing technology that will eventually scale up to millions of qubits. So it's fascinating to see all these different technologies computing with each other. Each of them has their advantages and drawbacks. And well, it's such an amazing ecosystem with many different options and technologies.
Definitely. It's actually an exciting time to be alive, I might say. My next question would be, where do you see quantum computing education heading in the next 5 to 10 years? Because you mentioned earlier also that education is very important in quantum computing, and we need a lot of youth to get involved in quantum computing to actually accelerate the speed of discovery in quantum computing. So
Yeah, for sure. Not only discovery, but also like development of useful applications.
yes.
And to me, that is kind of a very important and difficult problem
Mm-hmm.
because, as I mentioned before, I teach at different levels. I teach freshman, first year students, but also master students, PhD students, and I find very different interests and backgrounds and difficulties when learning about quantum computing. And many of my students do not have a background in quantum mechanics or even advanced mathematics. They are data scientists or they are software engineers, but they want to learn about
Yeah.
quantum computing. So I think it's very important to develop new materials, books, courses, software packages, different tools for people who are and will not be experts in quantum hardware or quantum error correction or quantum algorithms, like knowing all the details, but they want to use quantum computing to solve problems. So this is, I think, the main challenge. And I think that quantum computing educators, we need to focus on providing ways for people who are not interested and don't want to learn about quantum mechanics or advanced mathematics to get into the field and use quantum computers. Because, of course, now we have lots and lots of developers of applications that use artificial intelligence, but I guess only a small fraction of them really know what a neural network is and how it works. But they can use it to make amazing apps and to solve problems. So I hope that quantum computing also works in the future in that way. So people can use it without the need to learn what is, I don't know, Shor's algorithm or something like that. I mean, the actual details. So I think this is a challenge, and I see that many people are interested in learning quantum computing without the need to learn about quantum mechanics, for instance.
That's a great point you've made there. Actually, even I'm trying to make my own courses, so this is going to be great advice for me when I'm making that as well. I wanted to ask you, since now you've written the book, you have to go through a lot of material to really make a new book that is relevant for beginners and people from other fields to transition into quantum computing. So you've always got to revise and relearn certain things to make sure that it is perfect at the end. So how has writing this book now changed your understanding of any topic, any subject, anything?
Mm-hmm. Well, I think that what I've learned for all the material that we cover in the book is what is the shortest path from knowing nothing to completely understanding that kind of algorithm. Because there are many ways in which you can get to learn what is quantum teleportation or, I don't know, Deutsch algorithm or something like that. So what we try to find is what is the most straightforward way of getting to learn about these protocols and algorithms without having to learn a lot of things that you don't really need in the end. Because I think to me that is a nice problem to distill the essence of the protocols and algorithms so that you have all the details and all that you need to know, but nothing more than that. I think it was Einstein that used to say that you should keep something as simple as possible, but not simpler than that. And this is what we try to do in the book. And this is sometimes not so easy. And I feel that we have been able to do this in many of the cases. And well, this is up to the readers to say, of course, but I feel very, very proud of this kind of thing.
What tools or resources would you recommend to learners besides your book?
Well, I must say we have another book, okay? And
Yes,
in
yes.
fact, this book came out, or we wrote it after the first one, but I think it's better read before the other one.
Yes,
So
yes.
if you are new to quantum computing, I recommend you read first this practical introduction to quantum computing, and then the practical introduction to quantum machine learning and quantum optimization. But besides that shameless plug, I would like to recommend the videos and courses by this professor at Carnegie Mellon University that is called, who is called. I learned a lot from him. I mean, he's also a mathematician, and his way of explaining things is just incredible. It's wonderful, because one thing that he does that is very difficult is that he makes you think of what is going on, what are the question that you should ask, and he gives you all the tools to answer that question yourself. So he's giving you little bits and pieces of information so that you create your own solution to the questions that he is asking. And that is amazing. And he has like 2 or 3 different courses on quantum computing at different levels that you can find online for free. I mean, if you search for Ryan O'Donnell, he posts all his videos on his YouTube channel. And he also has courses on other related topics like quantum, computational complexity. And all his material is amazing. So that is, I learned a lot from him. I think that he's a much better teacher than I. So I would recommend taking a look at his material.
Sure, that's a new resource for me as well. I'll definitely check that out. I'll leave the link in the description box.
Oh, great.
Yes. If you could go back in time and give yourself any advice on how to start research in quantum computing, what would you give to yourself?
That's a difficult one. Maybe I would go back in time, and when I first was interested in quantum computing and decided maybe this is not practical, I should wait a little bit, I would knock me in the head and say, start now. Don't leave it for later. You are going to love this. Don't leave it for the future. But I had so much fun learning and discovering things and putting things together that I think that's the only advice that I would give to myself. Start as soon as possible.
That's great. One quote or idea or mindset that keeps you motivated in this rapidly evolving field.
Well, I don't know if you read this paper by John Preskill.
No.
John Preskill is a huge researcher in the field that is called, I think it's called the Nisk Era and Beyond or something like that. Or,
Okay, yeah, that paper.
Yeah, that paper is
Yes.
amazing. I mean,
Yes.
all the paper is amazing. But he has this section on variational methods and quantum machine learning, quantum optimization. You know that in the community there are there are different opinions on the actual usefulness of variational methods like the variational quantum eigensolver or the quantum approximate optimization algorithm. And there are some people that say, well, There are no theorems. I mean, that is true. There are no theorems that guarantee that with this kind of algorithm, you will get something that is better than what you get with classical algorithms. Okay, so as a mathematician, to me, that is painful because, well, we don't have like a compelling mathematical reason to use that kind of algorithm.
Mhm.
But at the same time, as a computer scientist, my background is both in mathematics and computer science. It's like, okay, this is a tool that I can use and I can try and see whether it works or not. And Preskill, in this part of the article or the paper, says, well, we also don't know that neural networks work better than other methods all the time. But, well, we have the results. And in fact, when I first started teaching at my university, I had this meeting with the head of the Artificial Intelligence Center, and he told me this was 2000 or 2001, something like that. And he said, we do not believe in neural networks. And that was a very accurate assessment at the time. Neural networks were not working 25 years ago. People were using all the different algorithms because neural networks were really not solving problems. But now we all know what you can do with neural networks. So this was encouraging, and reading this written by Preskin himself was very encouraging because, well, maybe now variational methods are not working, but who knows what will happen in 25 years.
Yes.
So that when I have like, well, sometimes we don't find how to apply this kind of algorithm to solve a problem. It's difficult. You don't get the results that you want. I always think of this reflection, and this makes me, well, a little bit more optimistic.
That's so true, and that's why I think people should not write off quantum computing right now because we're still in the nascent phase of the technology, and there's so much of scope and potential. Yeah. My next question would be, since you've written the book with Qiskit code in mind, how do you see tools like Qiskit evolving in the next few years, especially as quantum hardware scales?
Yeah. I think that, well, my main wish for Qiskit would be that it would become more stable, because I must confess that we had to change the code while
Yes.
writing the book several times. Because a new version of Qiskit is released, you
Yeah.
check your code, it does not work anymore, and then you spend like several nights trying to fix things. So this is my main, is the top, my top wish in my wish list for Qiskit. But this is something that I think has been improving. For instance, I think we work with Qiskit 1.4 or something like that, then while writing the book. Then Qiskit 2.0, 2.1. Well, and from 2.0 to 2.1, it was quite easier to immigration and all that. So I think this is getting better. But I guess that the main challenge is that if you want people to use a library or programming language, you need to make it very well documented and stable and all that. And of course, in a rapidly evolving field like quantum computing, this is kind of difficult. But I think that people at IBM are getting better and better at this.
That's true. All Qiskit users have the same feeling with you. Every other month is a new update.
Fingers crossed. Yes.
But at least they have a lot of resources, a lot of YouTube channel videos, and to guide students and researchers and everybody using Qiskit. So that's a good thing. My next question would be, what's your take on the race for quantum advantage? Do you think we're asking the right questions in the community right now?
Mm.
As I mentioned earlier, there are a lot of people who are still skeptical. What are your views on it?
Yeah, well, I think that's a very important question because I guess that uh, up to 5 years ago or something like that, everybody was looking for this quantum advantage. But now there are other questions that are being asked, like, well, can we get um, algorithms that need less energy
Mm-hmm.
to run and get the same results? Or in the field of quantum machine learning, can we get algorithms that can be trained with fewer data? And this is very important. For instance, at my research group here at the university, we work in the application of quantum machine learning to medical data.
Mm-hmm.
And it's very difficult to get data from medical doctors and from patients because, of course, this is expensive and you need, I mean, to take a lot of, to spend a lot of resources. So if you can get the same results but with fewer data, this is also very important. And this is not just quantum speed up, not
Mm-hmm.
just that. It's
Mm-hmm.
a different kind of question. So I think it's nice that people nowadays are looking into not only into quantum speed ups, exponential speed ups, and things like that, but also in what other benefits you can get from using quantum algorithms in different fields.
Yeah, that's a great point, actually. Um, what would you recommend for students or even people, industry professionals from other fields who want to go deep into quantum research after they've completed your book?
Well, nowadays, well, besides what I mentioned about the other book and Ryan O'Donnell's courses, nowadays there are many, many papers that are being published every day.
Mm-hmm.
I think it's nice to take a look at what is being published on the archive or on scientific journals.
Mm-hmm.
Even if you do not understand everything, you get a feeling of what questions people are asking,
Mm-hmm.
what kind of solutions researchers are trying to provide. And there are many, many directions in which the field is expanding. If you know a little bit of what people are doing, then you can choose which one is the one that you feel more motivated with or you feel more interested in, and then try to focus on that.
Yeah, that's a good point. How do you think the current educational efforts are going right now? Students are preparing for different quantum tools and all of that. How do you think the current scenario for the education sector is?
I think we need a lot more effort on this topic because we don't have enough people who can use quantum computers, who understand quantum algorithms, and if we want to provide solutions and applications, I think we will be needing much more people involved in the field.
Mm-hmm.
This is difficult because of what I mentioned before, that there are many people who come from different backgrounds,
Mm-hmm.
people who don't know about quantum mechanics or mathematics. They are developers, they know a lot about how to write great applications,
Mm-hmm.
but it's a change of mind when you have to think about quantum algorithms, because it's not just like porting your code to a different language. You have to completely change the algorithm. So I think that we need more educational efforts focused on software engineers and computer scientists, chemists who want to use quantum tools for solving problems in quantum chemistry, that kind of thing.
Mm-hmm. That's a good point. And what has surprised you in the recent last 2, 3 years about the progress of quantum computing?
I think that there is a lot of progress now I'd say in the last year in
Yes.
quantum error correction,
Mhm.
which is something that I didn't expect until farther in time. So to me, this is very good news because with quantum error correction, then we can run a lot of algorithms that are nowadays impossible to execute on actual quantum computers. And the advances in quantum error correction make me feel very, very optimistic. And I think this is a very, very important work that people are doing.
Yeah, true. This is a kind of fun question, but if you could go back in time and attend a single moment in quantum computing history, a paper presentation, a discovery, a debate, what would it be and why?
Woo. Well, I guess you know about this talk that Richard Feynman gave like 40 years ago, in which he said like, well, nature isn't classic, so
Yes.
we should build quantum computers to try and address these problems in quantum physics and quantum mechanics and quantum chemistry and all that. I mean that must have been amazing. I mean, because Richard Feynman was such a great scientist and a great popular he was so great at popularizing science. So I
Hmm.
think that should have been amazing.
Yeah. I think all quantum enthusiasts would like die to go and have a conversation with him any day.
Yeah, of course, of course.
And this is my last question. Where do you see yourself contributing next? Now that you've written a book, do you see yourself in research and policy, in hardware, in education, or maybe writing another book? What's your next
Hmm.
venture?
Well, I love writing books, and this is something that I've discovered. Well, as I mentioned before, I've always wanted to be an author, but now sometimes you have dreams, and when you make these dreams come true, they are not as you expected. But in this case, I loved the process of writing the book. Also, it was especially enjoyable with my co-author Samuel González Castillo, because he's such a great guy, and we had a lot of fun writing the book. So I hope in the future to be able to write another book. But I was thinking of something not related to quantum computing.
Hmm.
I also teach discrete mathematics and formal languages, and my PhD was on that topic. So I'm beginning to think about writing a book on that topic, but not quantum computing. But in quantum computing, now I need to develop new material for new courses, because my university is demanding me and my colleagues to create new courses in quantum computing for different people with different backgrounds. So this is something that I will be for sure doing in the next 1-2 years. And of course, I hope, although this is more and more difficult these days to be able to contribute in research. It's
Hmm.
more and more difficult because I have a lot of paperwork.
Hmm.
Spend most of my time now like writing reports and reading reports and attending meetings and things like that. But I would like to remain active, especially as I mentioned before, in the field of trying to find applications of neutral atom quantum computers in optimization and machine learning.
It's cool. That these are very interesting ventures. All the best for you, and I'm sure all of us will be keeping an eye for what your new ventures are going to whenever they're published. So thank you for making the time for us today. And it was a great conversation, actually. A lot of resources that I got to know about, a lot of advice that I'm taking back for myself as well. And I'm sure the viewers would have also enjoyed all your answers. And I've left a link to your book in the description down below as well, so they can check it out. They can start learning. I'm sure a lot of viewers have already bought the book and are already learning. So thank you for being here today and for taking up the time to have this conversation with me.
Thank you for having me. It was a lot of fun. Thank you.
Thank you.